Hey guys, what's up? Welcome back to the classroom. It's Mr. Low, and today we'll be looking at Chapter 7, Kinetic Particle Model of Matter. This topic is something that you should be familiar with because this has many overlaps with a similar topic in chemistry. Basically, we're looking at the particles that make up matter, okay, and we see that how temperature affects how all these particles behave in terms of the arrangement and in terms of the way they move. Okay, so without further ado, let's zoom right into it. The history portion for this part is I think it's something interesting that we should actually talk about. Okay, then we talk about the atom, right? So atom, we do know that all matter are made out of atoms. Okay, but how does this atom idea come about? Well, it began long ago, in ancient Greece, when this guy called Democritus, he was thinking about this question, right? A very intriguing question. If I have a piece of substance, a piece of matter, and I keep cutting it down, cut into half, right? So imagine if I have a block of something, I can cut into half, I can cut into a quarter, I can cut into an eighth, cut into 1 out of 16, and so on and so forth. Can I keep cutting it forever and ever and ever and ever? Well, he thought about it. The answer is no. Why? Because if we cut something forever and ever into infinity portions, what we will get is actually nothing. It will be so small until it becomes nothing. Okay, so if we cut that thing infinite number of times, you end up with nothing. But this is contradictory because if I gather all the different pieces of nothing together, by right, I should get back the original piece. But nothing plus nothing still gives nothing. Alright, so this is where Democritus concluded that, okay, there must be a limit whereby I can cut matter or substances into. Alright, that smallest limit, he called it the atomos, which we today known as the atom, which means the uncuttable. Right, so from this idea, later on scientists realized that yes, atoms do exist and they are the basic building block of all matter. Okay, and we're going to study them and the way they interact with heat energy, okay, in this chapter. So first of all, this is something that you may have already known, how to describe the arrangement of the particles and the way they move, okay, in solid, liquid and gases. This is the part that you have learned in chemistry. But in particular, we also want to look at this thing called forces of attraction between the particles, which we will see later. And then, something that's very important for this chapter, why some students don't get it, right? They don't do well, is because they don't understand that there is a difference between the particles and the matter itself. So there is a difference between the object itself or the substance itself and the particles that make it up. Okay, I'll talk about it more later. Okay, so first of all, we do know that for different states of matter, solid, liquid and gases, their particles behave differently. But here we are assuming, first of all, we are talking about the same type of substance to begin with, just that we're talking about the different states that this substance could be in. Okay, so for solids, for the solid state of any substance, most substance rather, particles are closely packed together. So the keyword here, let's highlight here, particles are closely packed together. I use a thicker highlighter over here. Okay, now here we are talking about the particles, and the way that the particles behave in turn will affect how the substance as a whole itself will behave, certain properties rather. Okay, so I say again, the behavior of the particle will affect the properties of the substance as a whole. So here we have to distinguish between, let me write it below. We have to distinguish between particles that made up the substance and the bulk material, which is if we look at the substance as a whole. Okay, so if I have a piece of solid stuff, right? Okay, if I have a block of, I don't know, a block of iron or something, Now the bulk material is the whole block, but when we zoom in, what we see is the particles of iron, which is in this case the atoms of iron. Okay, another thing to take note is that when I talk about particles, here we try to link between chemistry and physics. Sorry, I'm jumping a little bit here and there, but I think we should get the terminologies correct. So when we talk about particles, what do we mean? Who are these particles? They are either the atoms or molecules. CULES, depending on which substance we are talking about. So if we're talking about, for example, iron, right? Iron is an element. So iron, you know that we're talking about the atoms. But if we're talking about substances, compounds like water, right? So for example, here, for example, if we're talking about elements, then we're talking about the atoms. But for molecules, we're talking about compounds. Okay, so it depends on what substance, but for physics, for the purpose of physics, we are not interested in distinguishing between these two. We call them as particles in totality. So anyway, back to particles and bulk material. There is a difference between the material as a whole, which is what we call the bulk material, and the particles that make up this bulk material. Okay, so bear that in mind. Okay, so when we have a piece of iron, for example, when we zoom in, what do we see? We see these particles, which is the iron atoms. Okay, so first of all, for solids, okay, they are closely packed together. So because of this behavior of the particles, you have a property of the bulk material. Let me highlight this in green. High densities. Now, whatever I highlight in green, let me just take a note at the side. This is bulk property. That means we're looking at the substance, the property of the substance as a whole. Okay, so yellow color will represent particle behavior, and green will represent the bulk properties. Okay, we continue down the solid line. So first, just now we talked about the arrangement of the particles. Now we talk about the motion, right? How do the particles move inside a solid? So particles vibrate about their fixed positions. So this is something that we do already know. Okay, later we'll draw in the picture later, just as a recap. And a third thing that we have to know is this thing called forces of attraction between the particles. Okay, now these forces of attraction, later I'll talk about it more, but just give you a picture, I'll draw by the side. When I have a few particles near to each other, right? Let's not draw them too close. What happens is there is a bond or a force of attraction between each of them. So you consider them as rubber bands that bind them together. They are, imagine these black color lines as rubber bands, okay, between the particles. These fellas are what we call the forces of attraction. Just as planets and stars, they are attracted to each other via gravitational force, there is a force of attraction between these particles, be it in solid, liquid, or gaseous states. Okay, now this force of attraction exists between particles. Okay, so because of this strong forces of attraction for solids, the particles, you realize that they're held in place, they're held at fixed positions. This is why the particles can only vibrate about in fixed positions, because the forces of attraction between the particles are so strong. Roger that? Okay, now this is the particle property. Now let's look at the bulk property of the substance. As a result of having strong forces of attraction causing the particles in solid to be held down at fixed positions, you realize that solids have fixed volume and fixed shapes. Simply said, the particles are not free to move about. As a result, the volume remains fixed and the shape remains fixed. Okay, so you can imagine the particles are being held together in this square. The shape will be a square. It will not be anything else. okay, because they're just bounded to each other by this strong forces of attraction. So a reminder again that green color represents the bulk property of the substance, while yellow represents the properties or the behavior of the particles. Let's go into liquids now. Okay, so for liquids, the particles in liquids are slightly further apart compared to solids in terms of the arrangement, and now they're no longer held at fixed position, rather they are randomly arranged now. As a result of this particle behavior, you realize that as a whole material, liquids have high densities, okay, relatively high, but smaller compared to solids, of course, right? If I were to compare the densities of solid and liquids, clearly solids will have a higher density. Why? Because the particles are closely packed, okay, more closely packed, like packed sardines. Okay, now in terms of movement, now the particles are free to move about, okay, whereas earlier on in solids, the particles are held in fixed positions, they can only vibrate about their fixed positions. So why is it that now in liquids the particles are free to move about? So now we're going to study the forces of attraction. There are some attractive forces, some between the particles, but clearly not as strong as solid. Okay, clearly not as strong as the attractive forces in a solid. Now, as a result of this strong but not as strong attractive forces of attraction, as a whole, the bulk property of liquids is that they have no fixed volume and no fixed shape. Okay, and you can see that because, well, the force of attraction between the particles in a liquid are not as strong, the particles are now free to move about. As a result, the whole liquid as a bulk material does not have a fixed shape or a fixed volume. It is free to expand. Okay, we now come to gases, which is the very extreme end. On the other end, the particles are far apart and randomly arranged. Now, as a result of being widely arranged, far apart from each other, the bulk property is that gases have low densities. Why is that so? Why is it that they have very low densities? Recall that density equals to mass over volume. When the particles are far arranged from each other, they are far apart from each other, what happens is you see that the volume increases. As a result, the density goes down. This is the reason why. Okay, in terms of movement, we see that the particles are free to move about, of course, at very, very high speeds. So now the particles, they are not only further apart from each other compared to liquids, but at the same time they are also more free to move about, and they move about at very, very high speed. Okay, now why is that so? We go down to the attractive forces and we see that the attractive forces between the particles are very weak. This time they are very, very weak. Okay, let me redraw this. They are very weak. Alright, now as a result of this very weak force of attraction, you see that they are now free to move and that they can move about at high speeds. So they're not as strongly bounded to each other as per liquids and solids. So for the bulk property, gases have no fixed volume and no fixed shape, just like liquids. Okay, so both liquids and gases have no fixed volume and no fixed shapes, unlike solids. Okay, and you can explain it in terms of the attractive forces between the particles. So this table summarizes the behavior of the particles in yellow, as highlighted in yellow, and the bulk property of solid, liquid, and gases as highlighted in green. So do note the differences between the behavior of particles and the properties of the bulk material. So we summarize that table here. We see that, okay, here there is the behavior of the atoms, and then you have the physical property of the state. Here I'm referring to the what I call bulk property, which is the property of the substance as a whole, not looking at individual particles. So when the particles are closely packed, you realize that the substance itself has high density. Why? Again, because density equals to mass over volume. So when the particles are closely packed, the volume goes down, density goes up. Okay, next we look at if the particles are far apart. This is the opposite, right? Exact opposite. So you have low density. Okay, and then the opposite is true. Density is mass over volume. So when the particles are far apart, you realize that the volume goes down. Sorry, opposite. The particles are far apart means that the volume is now increased. Therefore, density goes down. Okay, now, next, when you have strong attractive forces, as we discussed just now, when we look at the role of the force of attraction, you realize that the result is whether the substance as a whole has a fixed volume or fixed shape or not. Okay, so when you have strong attractive forces, you realize that the bulk property of the material as a whole, it has fixed shape and volume. Okay, because the particles are held at fixed positions. Okay, so they are not free to move about. As a result, the bulk property, the material as a whole, okay, it has no fixed shape. It has a fixed shape and volume. So clearly we are talking about solids here. Okay, so on the other hand, liquid and gases, they have weak attractive forces, weaker than solids, of course. So here we have no fixed shape. And no fixed volume as well. Okay, no fixed shape, no fixed volume. So again, behavior of the particles. Instead of atoms, you might want to change this to particles. No fixed the behavior of the particles resulting in the bulk properties. Okay, now this part is a simulation that I want you to try on your own. I will not go through this portion, but rather I will just summarize the learning this part for you. Now, if you do look at the simulation as a whole, what you will see is that what happens to the particles, how do they behave when we increase or decrease the temperature? Okay, now in the previous section, we do recall that the particles are always moving. Either they vibrate about fixed position or they are free to move, okay, at different speeds. So they are indeed moving regardless of what state the material is in. So because the particles are moving, you realize that they do possess some form of kinetic energy. Right? That's of course. Anything that moves, it possesses kinetic energy, or rather we can also say that energy in the kinetic store. Okay, so remember this is the last chapter, previous chapter, energy in the kinetic store. We talk in terms of store. Okay, so when we increase the temperature, or rather when we heat up the matter, we are supplying energy to the substance. What do we observe? Okay, in terms of the particles, we observe that the particles move faster. Or you can talk in terms of move around more vigorously. Okay, so when we heat up the matter, we observe, this is what we see. We see that the particles in the simulation move faster or more vigorously. We therefore conclude that from the observation that the particles possess more energy in the kinetic store. So now we're looking at the kinetic energy, or the energy in the kinetic store of the individual particles. Okay, so this is the process when we heat up the substance. What happens to the particles, and what can we conclude about the energy, right, that the particles possess? Okay, now of course when we do the opposite, now we're doing the cooling portion, right? Once we cool down the matter, opposite, we observe that the particles slow down. Or you can say move less vigorously. Now, when we observe that the particles slow down, in terms of energy now, we can conclude that the particles lost energy from the kinetic store, of course, because they move slower, you see. Right, so when you cool the substance down as a whole, what you're actually doing is you're removing energy from the kinetic store of the particles inside the substance. As a result, later you will see that the temperature of the substance goes down. This is something that we do know from our common sense, right? So later we will see what is the relationship between this kinetic store of the particles and the temperature of the bulk material. Again, you see the relationship between particles behavior and the property of the bulk material. Alright, in the next section of this chapter, we will be zooming in to look at the energy that the particles possess. Okay, basically it's split into two different parts. One, we call it the internal Ke, and we also have the internal Pe. And the sum of these two, that means if I were to add up the internal Ke and internal Pe, we call it the internal energy. It's that simple. We're looking in detail why these particles possess these two types of energy. Right, so without further ado, let's zoom into the very first type, internal Ke. Alright, so as described earlier in this video, particles are always in constant motion. In particular, the motions are actually random, right? They move all over the place in random directions at random times. So, for instance, you see that in solid, we do know that the particles are always vibrating about fixed positions, right? But for liquids and gases, the particles are free to move about. Okay, either ways, the particles are always in motion, and we do know that any object that are in motion, any object that is in motion, possess kinetic energy. Okay, so they possess some form of kinetic energy as well for these particles. Okay, to distinguish between the particles Ke and the Ke of the everyday object, like your chairs, the ball, cars and whatnot, we call this kinetic energy internal Ke. So the internal represents for the particles instead of for everyday objects. Okay, so again, because particles are always in constant random motion, they possess internal Ke. So this part is quite simple. Okay. Yeah, earlier in the video, we mentioned how heating the substance causes the internal Ke, causes the particles to move faster. That is when we look at the simulation earlier, we see that, okay, as we heat up the substance, we observe in the simulation that the particles move faster, and from there we conclude that there should be more energy in their kinetic store. Now we know it as internal Ke. Okay, now when we heat up a substance, okay, so this is by heating. This is by heating, right? So earlier we know that, okay, the particles move faster, the Ke or energy in their kinetic store, which we now know as internal Ke, increases. And what happens is, what we observe is that the temperature of the substance increase. So this is the bulk material. This is for the bulk material, right? Okay, we do not measure temperature of the particles. There is no such thing as temperature of the particles, but there is only the temperature of the bulk material. So in our everyday life, what we can observe in our everyday life is, number one, when we start heating a substance, we jump straight into the temperature increasing. That's something that we can measure and we can observe in our everyday life, right? So that's why I say we observe that. But what goes on in between that we don't really see in our everyday life is this, right? The heat energy, the energy that is input into the substance by heating becomes the internal Ke of the particles. Okay, so once the internal Ke increases, yes, the particles move faster. So this is what happens at the microscopic level that we don't often see. To see what happens at a microscopic level, we need super powerful microscopes in order to see that. Okay, now on the other hand, in the opposite direction, when thermal energy is released, this is when cooling happens. So when we remove energy from the substance, we can observe that the temperature decreases. So again, this is for the bulk material, bulk, so the substance as a whole. So the bulk material temperature decreases, but what goes on in between is that the energy lost to the surrounding when we cool the substance is taken away from the internal kinetic store of the particles. So the internal Ke of the particles drop, they start to move slower, and as a result, the bulk material's temperature decreases. This is something that we cannot observe in our everyday life at the microscopic level. Okay, so this is the picture, how energy changes results in temperature changes. This is what goes on in between. Okay, so let's look at this question. Comparing solid, liquid, and gaseous states of the same substance, in which state does the particles have the most internal Ke, and explain in terms of the motion of the particles. Okay, so we compare again, right? In case you forgot, we can always go back to the beginning where we look at the motion of the particles. In which state is the particles moving the fastest? Because we do know that the faster the object or the particle moves, the higher kinetic energy it possesses. So clearly it's gases, right? Okay, so the answer here very clearly should be in the gaseous state. So in the gaseous state, okay, the particles have the most internal Ke compared to solids and liquids. And why is that so? Let's explain in terms of the motion of the particles. So in the gaseous state, so basically the particles move the fastest. As compared to liquids and of course compared to solids, right? Okay, therefore not higher but rather highest, right? Most have highest internal Ke. So we compare the speeds, the moving speeds of the particles to compare the Ke. Alright, but one thing to note over here is that there's something that I did not mention, and I think we should actually write this down. Okay, when we look at a substance, let's say this solid over here, all the particles are vibrating, of course, and they do possess some internal Ke, but they do not possess the same amount of internal Ke. again, they do not possess the same amount of internal Ke in the same substance. Rather, it is a distribution. Some particles have higher internal Ke, some particles have lower internal Ke. Okay, so let's take a note over here. The internal Ke of the particles differ. Okay, so that means each particle, they do possess slightly different amount of internal Ke, which also means that the particles will not be moving at the same speed throughout the whole bulk material. Okay, so because the internal Ke of each particle in a bulk material are different, we can only talk about the average kinetic energy. So let's continue the note here. Okay, so we can only talk about the average internal Ke because each particle has different amount of internal Ke. Okay, let's move on. Right, so next we look at the internal potential energy, EPE. Now earlier in the chapter I mentioned that the particles are held by strong forces of attraction. Okay, these are like rubber bands, invisible rubber bands that exist between particles. They do attract each other through this forces of attraction that we cannot really see. Alright, so because of these forces of attraction, it gives rise to this idea called internal PE. So imagine this interparticle forces of attraction, which in chemistry you may have called it intermolecular bonds, but here we call instead forces of attraction. Between the particles, they behave like rubber bands or springs, whatever you like to see it. Okay, so it behaves the same way. When you stretch the rubber band or the spring, there is elastic potential energy, isn't it? Here it behaves the same way. When you stretch these forces of attractions, there is it gives rise to this internal potential energy. Alright, so again, they behave like springs. So instead of having elastic potential energy, they now have they have this internal potential energy. They behave like, okay, so we call that internal potential energy. Okay, so instead of EPE over here, we now have internal potential energy, just like springs. Okay, don't write this arrow down, never mind. Okay, so remember that when substances change state, that means melting or boiling, okay, when you heat them, the particles do move further away from each other, right? So this is one thing that you should remember from your chemistry or earlier in this topic. Okay, they move further away from each other. So as they move further from each other, so let's draw in the forces of attraction. I use a solid line, of course. Okay, so as the particles move further away from each other, of course this so-called rubber band will be stretched. Okay, so we call it overcoming the intermolecular force of attraction in chemistry, but in physics, when we are concerned about the energy, what happens is from here to here, the internal PE increases. Okay, so as the particles move further away from each other, they stretch this so-called intermolecular bonds. And as a result, just like a stretch spring, the internal PE increases. Okay, so let's see what happens here. Again, a flow chart here. When a substance melts or boils, that means changing states here, the particles move further away from each other. As a result, internal PE increases. Okay, so this is the heating path. Again, when we heat the substance. On the other hand, when we cool the substances, you see that, okay, it can either freeze or condense depending on which state it was in. So when it freezes or condenses, the particles come closer to each other. They are so-called being overcome by this intermolecular force of attraction, as you may have learned in chemistry. As a result, internal PE goes down. Okay, so we combined earlier when you talk about internal KE and internal PE. When you heat a substance, it can either result in, over here, increase in internal KE, or when you heat a substance, it can cause a increase in internal PE. So I say again, when you heat a substance, it can either result in increase in internal KE, or when you heat a substance, it can result in an increase in internal PE. So it depends, it will be either or, which we will see later when it happens. When does internal KE increase, or when does internal PE increase? But before we go into that, last but not least, this thing called internal energy, very simple, it's just the sum of the internal KE and the internal PE. That's it. Okay, so the energy that particles in a substance they possess is a combination of these two, internal KE and internal PE, which we call it internal energy. Okay, so for everyday objects, the sum of the KE and PE, we call it mechanical energy, but for substances we call it internal energy. Okay, that's it. Okay, for these two types of energy. Okay, now in the last in this should be the last portion, yes, the last portion of this chapter. Okay, we are looking at trying to explain when does the internal KE increase and when does the internal PE increase when we heat a substance. Okay, it's kind of either or. Okay, now so let's look at the objective here. Okay, we will explain the rise in temperature of a body in terms of gaining of internal KE of the particles. So again, this rise in temperature of this body here refers to the bulk material. So we'll try to explain properties or behaviors of bulk material in terms of the particles, in terms of the behavior of the particles. Okay? And then we have to know how to identify this thing called heating and cooling curve, which we will see later what it's actually about. And then explain in terms of internal potential energy why there is no change in temperature when there is a change in state. Okay, so we'll go into more details later. Okay, basically we're explaining temperature changes of the bulk material by looking at the energy at a microscopic particle level. Okay, so first of all, heating curve. Okay, heating curve is a graph that demonstrates, or rather it shows what happens to the temperature of a substance, of a bulk material, when it's being heated. Okay, so in this example, we are starting from solid state. So in part A here, this is solid. So we're starting off with a substance in the solid state, and we're starting to heat it up. Okay, common sense tells us that when we heat up a substance, the temperature should increase. But if we do measure the temperature as you heat up a solid, in this case we're looking at ice in particular, which is water, you will see that there are two parts whereby the temperature does not increase even though you are constantly heating it. That means I'm constantly supplying heat to this substance, but there are two portions whereby the temperature does not increase even though it's constantly receiving energy from the heating. Okay, so we take a note here, no changes, or rather no increase in temperature. No increase in temperature. So you see this for part B and part D. No increase in temperature even though energy is constantly being received. Okay, this is what we observe. If we do the experiment, right, this is what you would see. And which brings us the problem. Why is it that the temperature is not increasing even though we're heating it? Okay, so to explain this, we have to go down to the microscopic level. Now, for NA science, you do not have to know, NA physics, you do not have to explain. Okay, you do not have to explain why. You just need to know that, number one, there is these two portions whereby temperature will not increase if I start from solid state. Okay, and looking at the temperature here, that these two portions B and D happens, let's observe 0 and 100 for water. What does it remind you of? Okay, it should remind you that 0 degrees Celsius actually is the melting point, and 100 degrees Celsius clearly is the boiling point. Okay, so for NA physics, you have to know two things. Number one, heating curves, a few things, not just two. Number one, a heating curve looks like this. There are two portions of the heating curve whereby the temperature remains constant, does not increase. These two portions correspond to the melting point and the boiling point. That means the temperature of which these portions B and D happens is the boiling point and the melting point. So very clearly, part B is when melting occurs, and part D is when boiling occurs. Okay, so when you see when the substance is melting or is boiling, you will observe that the temperature remains the same. Okay, so let's highlight here. B and D are the parts of the heating curve that corresponds to the melting and boiling process. So here we try to explain why. For NA physics, this part you can skip, but good to know. Okay, so the question here is, why does the temperature not increase during the melting and boiling point? Okay, so first, you remember that during melting and boiling, the particles move further apart. From the earlier portion, we see that internal PE increases. So the energy transferred to the substance in terms of by heating is being converted to the transferred to the internal PE store. Now when that happens, there is no increase in internal KE. As a result, you see that the temperature remains constant. So this is something that we have to take note here. Temperature, when you say temperature of a bulk material, or rather a substance, right? What are we trying to say? The temperature is actually a measure of the average internal KE. of its particles. Okay, so this is something that you have to take note. Temperature is a measure of the average internal K of the particles. So the higher the temperature, clearly we do know that the particles move faster, therefore the average internal KE is higher for the particles. So in this portion, during the melting and boiling process, here I'm just showing the melting portion. During the melting and boiling process, what happens is that the energy gained by the substance is being converted into internal PE as the particles move further apart. As a result, the energy is not being transferred to the internal KE store. As a result, the temperature remains constant. Okay, no gain in internal PE, internal KE, so the temperature remains constant. Okay, so what happens here? For the other parts like A, C, and E, okay, what happens is you see an increase in temperature. So therefore, you know that there is a gain in internal KE for the particles. Okay, but before we even move on, right? Since I mentioned that in part A is solid, the state of the substance is solid. What happens at C and E? Well, after melting, the state here should be liquid, and after boiling, the state here should be gaseous. Okay, now of course here we are starting off from solid, so it will be a solid, melting, liquid, boiling, then gaseous. Depending on the question may start off from liquid state, so you only see this portion of the graph. Okay, now after gaseous, what happens? You will just keep on increasing, at least for our syllabus. Okay, you will just keep on increasing. Okay, so let's look at the processes A to E again, which is from this graph, A to E. From A, at the start, it was solid, yeah? Okay, it was heating up, and then there is an increase in temperature we observe. So therefore, we see that thermal energy is mainly converted into internal KE. Okay, so for sections B and D, where there is a change in state, you notice that there is no change in temperature. Energy is mainly being transferred to the internal PE portion. The rest, A, C, and E, energy is being transferred to the internal KE store. Okay, so this is the difference between the part whereby there's no change in temperature and the rest. Okay, cooling curve is the exact opposite, yeah? So we see that again there are two portions here whereby temperature does not decrease even though cooling is constantly happening. So clearly they correspond to the two opposite processes change in state. At 100 degrees Celsius, the opposite of boiling is condensation. Right, the substance is changing from gas to liquid state. And then back at 0 degrees Celsius, the opposite of melting is freezing. Okay, so at these two portions, G and J, no change in temperature again. Again, they correspond to changes in state, STATE. This time round, it is condensing and freezing. Okay, so starting from F must be a gaseous state. Or rather, the substance at point F should be gaseous state. After condensation, this is liquid. And after freezing, clearly must be solid. Okay. After solid, what happens? Again, it will constantly go down. The temperature will constantly go down over time, you know, if you keep cooling it. Okay, so main points here for NA science, the cooling curve has two portions whereby temperature does not change even though the substance is constantly being cooled down. They correspond to the condensing portion and the freezing portion. Okay, now we try to explain why this part not applicable or not necessary for NA science. When we remove energy from the bulk material, from the substance, as the substance change state, let's say for freezing, solidification, right? What happens? No change in temperature, because the internal PE of the substance is being lost to the surrounding, okay, through heating, or rather through cooling. So there is no decrease in internal KE. So from this portion, during the freezing process, energy is being taken away from the bulk material. The energy comes from the internal PE of the substance. No energy is taken away from the internal KE. Alright, so when the internal PE decreases, you observe that the particles move closer to one another. Alright, consistent with the picture that we know. From gaseous to liquid, the particles come closer. From liquid to solid, the particles come closer to each other. So during the coming together process is because energy is lost to the surrounding. As a result, the particles are being so-called overcome by these intermolecular forces of attraction. The energy lost comes from the internal potential store. Okay, so this table is the opposite of the table at the top. Here, on top is cooling. Now this is on top is heating. Now this is cooling. Okay, so same thing to note over here. There are two processes whereby there are no changes in temperature. The energy that is lost to the surrounding mainly comes from the internal PE. That's it. So to sum it up, this is what happens. Okay, going up and going down is the same thing, just that the main thing to note over here is the change is during the change in state phase, the temperature does not change. Alright, so that's it for this topic. Hope to see you back in class. Take care.